So the last section of chapter 16, 16.4, linear and angular speed, has to do with putting things into practice and a lot of just formula uses. But it's also knowing when to use the formulas. So let's go over them real quick. The top one on the left, we have speed equals distance over time. And when it talks about speed, it's talking about a linear speed. And then you could, next to it, you could see it's also written as V equals S over T. And V refers to velocity. S actually stands for distance. And T, that stands still for time. So velocity equals distance over time. Now, if you think about what that really kind of means, because velocity is really like, the speed and the rate. This is just a rearrangement of the formula we've talked about several times. Distance equals rate times time. Um, if we take a look at the diagram over here, and I label P as a point on the angle going through the circumference, O is the origin, and B is the stationary point right there. And I have this angle right here moving through. This right here refers to the distance. So this is S. And if you remember back to 16.2, that's really the arc length, right? Because it's a portion of their circumference. So that's why they label it that S, because it refers to that arc length again. So that's what's happening here. So as that angle is moving, right, around the circle, you're increasing the arc length. Okay. The other equation that we use as well is angular speed. And that says omega, that's that kind of W looking shape, equals theta over time. And remember, theta is in radians and it refers to the angle. And that T refers to time. Angular speed refers to the measure of how fast angle POB is changing. So, how fast it's kind of going around that circle. Now, you kind of see a couple variations of this down here, okay? Now, if we look at this first one, it says velocity, I'm going to kind of rewrite this, velocity equals distance over time. Well, think about this from 16.2. We know that distance, or the arc length, is also theta over r. So that's how we get that substitution over t. And we can separate this out to be r times theta over t. And we also, from the other chapter, know that theta over t, or I'm sorry, just from above, theta over t, right up here, equals omega. So radius times omega, which is that angular speed. So what that actually does is it produces lots of variations of this. So velocity, which we start with the original, is distance over time. Velocity is distance over time. And then velocity is radius times theta over time. So radius times the angle over time. And finally, we get another one. We get velocity also equals the radius times omega, which is the angular speed. So again, we have three different versions of this. So now it's just kind of putting this all in practice. This first one says, suppose that P is on a circle with radius 15 inches. And the ray OP is rotating with angular speed of pi over 12 radians per second. So again, you can refer to that diagram that we had at the top of the screen. So the first question is find the angle generated by P in 10 seconds. So what we're going to do is we're going to think about what we're given. We know that the radius is 10 inches. We know that the angular speed is going to be pi over 12 radians per second, and our time is 10 seconds based on part A. Okay, find the angle generated by P in 10 seconds. So the question says find the angle, which is finding theta. So I kind of think about what uses these, and the formula that uses these are angular velocity equals theta over time. So I just put in what I have. Pi over 12 equals theta over 10. I'll multiply both sides by 10, and I get 10 over 12, which is going to reduce to 5 pi over 6, which equals theta. So I'm looking for this in radians at this point, so it would be 5 pi over 6 radians. I want the unit of measurement. Otherwise, if you wanted it in degrees, I would multiply by 180 over pi. Okay, so part B asks us to find the distance traveled by P along the circle. So if you're thinking about it, the distance traveled along the circle, okay, so distance around the circle, that's an arc length. So that's what we're trying to find. We're trying to find the arc length here. Again, I wrote down what's given. Forgive me for the terrible handwriting. So I see what's given. I'm going to find S. We know that we can find the arc length, again, based on the formula from 16.2, is the arc length equals radius times theta. So then we have 15 times 5 pi over 6. If I multiply it and reduce it, so these right here could be reduced to 5 over 2, I will get 25 pi over 2. And then this is inches because it is the arc length. And the last part of this, it says find the angular speed of P in inches per second. So again, we're looking for that speed of which that angle is traveling. And so the formula that uses, and again, I rewrote now all the new information. You notice that I added now the arc length. But I can find velocity by the arc length over t. So the arc length is 25 pi over 2, and that's divided by 10. Remember, when dividing by a fraction, I'm multiplying by the reciprocal. So I'll multiply by 1 over 10. That's going to reduce to 5 over 2. So I get 5 pi over 4, and that's inches per second. And that's going to be your angular speed. So number 2 gives us some information. It says a belt runs a pulley of a radius 6 centimeters at 80 revolutions per minute. Okay. So remember what a revolution is. A revolution is one full rotation. Okay. So letter A says find the angular speed of the pulley in radians per second. Well, what I'm going to want to know is that if I have 80 revolutions, think about what that means, how many times around. So that's 80 times around, and we know that going around the circle is 2 pi radians. That means that it actually goes 160 pi radians per minute. Okay, because it does 80 of those, so I need to multiply 2 pi times 80. Now, I can find the angular speed by just plugging it in. So it's 160 pi over 6. Sorry, 60. Because we want this in seconds. So instead of per minute, there's 60 seconds. So that's why I put the 60 instead of the 1. That's going to reduce down to 8 pi over 3. So that's radians per second. Part B is asking for the linear speed of the belt in centimeters. So if I know that the radius is 6 and I know that the velocity, angular speed is 8 pi over 3, all I have to do is plug that in there. And what we're going to end up getting is about 16 pi, which is approximately 50 centimeters, and that's per second.